Hi, everyone. We are going to soon start lecture number 12. I think last time I left a bit of some complex numbers situation, which I will fill in today. And briefly, what we plan to do today is, as I said, a little bit about complex numbers and matrices. We'll talk about the Bloch sphere. We'll talk a little bit more about the IBM composer, entanglement, and most importantly, today we're going to discuss very, very in-depth the concept of teleportation. It's important for me that we finish this course and you all understand because it's a bit of a tricky protocol. At the same time, once you understand it, you blow up with it's just unbelievable. The concept of teleportation. So let's just very quickly talk about complex numbers. With your permission, please let me know if you see my screen. I think you do. Sorry. Just give me a second. Okay. Okay. So, I'll do the minimal stuff required to discuss complex numbers. And basically, a complex number is something that looks like this. Where A and B are real numbers, and I is simply the square root of -1. That's all. I mean, we're not going to go deeper into complex numbers. What I do want you to note is a very important operation on complex numbers, which is called the conjugate. And if Z is equal to A plus BI, then Z conjugate is equal to A minus B. So the only thing we do when we conjugate a complex number is put a minus before its imaginary part. That's all. And if this is the case, then you can always see that Z times Z conjugate would be A square. The BI's will delete themselves and plus B square. So Z times its conjugate is a real number and it's equal to A square plus B square. So just as an example, okay. So let's say we have a number like, Z equals 5 minus 4i. Then Z conjugate will be 5 plus 4i. And Z times Z conjugate will be 25 plus 16, which is 41. Okay, any questions? Okay, that's really, really simple. Let's move towards more interesting things. But maybe before complex matrices, I want to discuss a little bit the whole definition or Copenhagen interpretation, which we've discussed. And if you remember, we said that if we have a system that can be in, sorry, let me just fix it a little bit. That can be in, let's say, 3 places. Let's call this 1, 2, and 3. And when I say that the system can be in one of these 3 places, imagine that we throw a ball a ball is coming from here, and we know it's going to fall somewhere. But we know for sure that if we are going to do a measurement, we will not find the ball here, and we will not find the ball here. It will be either here, here, or here. So if I do a classical measurement on this system, it will be for sure in 1, 2, or 3. The quantum interpretation of this situation is as follows. Our wave function is equal to A1 times phi1 plus A2 times phi2 plus A3 times phi3. So what it means is the following. Before we did the measurement, our wave function, which is a complex number, as you will now see, is a superposition. It's a combination of the three. Now, the phi1, phi2, and phi3 are the states of the system. And these constants, very important, are imaginary numbers. And one other thing which is really important is that if we want to know what would be the probability after I do a classical test. So before I did the test, this is the state of the system. It's a superposition of the three possible physical states. Once I do a test, let's say I want to know what would be the chance to be in 3, it's very simple. Just take A3, multiply it by its conjugate, and you usually write it like this. And this will be the probability of having the system being in state 3. Now, one should ask, how do you know what A1, A2, and E3 are? And the answer is, this is where the physics comes into play. So if this ball flew in this area, there's a very good chance it will fall in 3. In this case, A3 will be bigger than A2 and A1. Okay, so the physics determines the sizes, the actual numbers, A1, A2, and A3. But once we do the test, once we do the measurement, and let's say the answer was 3, the wave function collapses, and now psi will be simply phi 3. In other words, now we have a very boring situation where the function is not in superposition anymore. The beautiful of quantumness has disappeared, and now we have this shadow of a situation where we just have a classical boring system in phi 3. But it's very important that if we had other measurements, we could find it in phi 2 and in phi 1, all according to the numbers of A1, A2, and A3. So to summarize, before we measure the system, we have a superposition. That's the beauty of quantumness. Once we measure, the wave function collapses to one of the real states that can be measured, and we get a classical system, a classical particle in a classical place, and nothing is interesting anymore, unless I do some quantum operation on it, as we'll see in a minute. But if we leave the system as is, that's it. It will stay here forever. Are we okay? Okay. So let's talk a little bit about complex matrices. And in the same way that we have a conjugate on a number, we also have a conjugate on a matrix. So let's say we have a matrix A equals, I don't know, 1, I, 2 minus I, and 3. Okay? Let's say this is my matrix. The conjugate of a matrix is usually, it looks like a cross. Sometimes it's called the Hermitian conjugate. Hermit is a monk, Nazir. That's probably why they have the cross. I'm not sure about it. But what you do is two things. First of all, you do the complex conjugate. In other words, the matrix will be 1. Instead of I, we have minus I. instead of 2 minus I, we have 2 plus I. And 3, of course, stays the same. And now we do the transpose, the usual transpose, shichluf, as they say in Hebrew. And the result will be 1 minus I, 3, 2 plus I. Very simple, okay? When you want to conjugate the matrix, you transpose it. In other words, you make all the rows be columns, and then each element of the matrix goes through a regular conjugation. In other words, the I becomes a minus I. Just as a nice exercise for you, see that if you have any matrix, complex matrix, and you multiply the matrix by the transpose of the matrix, does anybody know what we will get for sure? I don't know anything about the matrix, any complex matrix in the world. What happens if I multiply it with the transpose of the matrix? I will get another matrix, which will be real. In the same way that a number, when you multiply it by its conjugate, becomes a real number, remember? The same thing happens with matrices. Okay, now I want you to pay attention to this critically important line that I have here. Very easy to prove. You can do it easily by just playing with sigmas, but it's critical to understand what it means. If you multiply two matrices and you conjugate the result, it's exactly like conjugating the second one, multiplying it by the conjugate of the first one. I have here a very simple example. Let's say I have a matrix A, which is equal to this, B is equal to this. So the first thing I do is I multiply them to get AB, and I get this matrix. And now I transpose this matrix, and I get this matrix after transpose. Now let's see if it's really true. So let's take the original B and transpose conjugate it. I get this. I do the same thing with A, and I multiply it the other way around, and of course I get the same result. Very easy to prove, 3 lines of a proof, but it's a very, very important thing to remember because we will use it a lot. Sorry. Lastly, something that all of you know, especially the physicists, how do you find the length of a vector? So let's say we have a vector x, y, z. Let's say it's complex. Now I do the complex conjugate of the vector. So as you see, each number becomes complex and the row becomes a column. And if I want to multiply V transpose conjugate times V, I get something very interesting. I get x squared plus y squared, I mean the conjugate squares. In other words, I get a real number, and it's very similar to length. You can see that it's actually the Pythagorean square of the vector. So any vector, once multiplied with its Hermitian conjugate, actually gives us the length square of this vector. Finally, let's do a nice trick. And let's say that we have a wave function, which is called psi. Now, as I showed before, if I multiply psi transpose by psi, I will get its length. And it's a real number that is, of course, larger than 0, unless it's 0. But what happens if I take this function psi and multiply it by u? Oh, I forgot to mention, I think I missed that one here, sorry. A very important matrix is called a unitary matrix. It's a complex matrix, and a unitary matrix is the one that follows this rule. Okay? It's very similar to the rotation matrix from non-complex linear algebra. But if you have a matrix and you multiply it by its transpose and get a 1, a unit matrix, you have a very special matrix, a critically important matrix, which is called a unitary matrix. To those of you that study quantum mechanics, you know that there are 2 kinds of matrices, Hermitian matrices and unitary matrices. In this course, we'll only talk, unfortunately, about unitary matrices. And what I want to show very easy and simply, what is really the nature of a unitary matrix, and it's what we see here. So we said that we have a certain vector, a wave function, which is called psi, and we all agree that if we multiply it by Hermitian conjugate, we'll get the length of this vector, and it has to be a number which is larger than 0. Now I want to do something very interesting. I want to create a new vector, phi, that you see here, and phi is our original vector multiplied by a unitary matrix. So I took my original vector psi, I multiplied it by a unitary matrix, and now I'm interested in understanding what the new vector will be. In other words, what I want to know now is what is the length of the new vector. The old vector length was L, but now it's changed because I changed the vector to phi. I multiplied it by a matrix. And you remember that when we multiply a vector by a matrix, we get a new vector. So let's see what happens. So we know that phi is equal to the unitary matrix times psi. But what is phi conjugate? Oh, that's very easy. Remember that I gave you a formula before. If you want to conjugate the multiplication of two matrices, just conjugate each one of them and multiply them the other way around. So this is what happens here. Phi is equal to u times psi, but phi conjugate is equal to doing the conjugate on each one of them and doing it the other way around. So this is now phi dagger or phi conjugate. Now, if I want to know what the length of the new vector is, it's very simple. It's phi dagger, which is this, times phi, which is this. But look, when we multiply u dagger times u, we know that it's 1 because we defined it as a unitary matrix. So if this is the unit matrix between them, I get something very interesting. The same length. So phi dagger times phi is exactly like psi dagger times psi, which is L. Okay? And this is really, really a critical property of unitary matrices. They do not change the length of a vector. They rotate the vector in the complex space, but they never change its length. And I think now we are more or less ready to go back to our presentation. But before that, just to remind you that we defined psi in a two-state system is something like this: A times state 0, B times state 1. We also showed that it's exactly like showing it in this way. Sorry. And if it's the same, then we can multiply A inside and B inside, and we get here A and B. But in the original lesson last time, we mentioned that A and B were just real numbers. But now we're already adults, and I can tell you that A and B can be complex numbers. And this makes things a little bit complicated because this vector here has really two complex numbers, A and B, right? If A here and B here are complex numbers, then it means that psi is a complex vector with two elements. But wait, if this is the case, we already mentioned that the complex number, like A here, is really two numbers because it's a real number and imaginary number. So A is really A1 and A2, and B is really B1 and B2. So we actually have four real numbers that determine this little vector, which we call qubit, okay? So now we see that real qubits are really dependent on four different numbers. They have 4 degrees of freedom. Scary, but I have good news. Actually, we can reduce these 4 numbers to 2 numbers. And the reason we can do it is because, first of all, we know that a squared times b squared equals 1, because that's the length of the vector. okay? And the probability of a squared plus b squared has to be 1. So we already killed 1 out of the 4. And the other one we kill in a different way. It's called the global phase. I will not get into it, but I'll just tell you that it's possible to take these 4 numbers which determined our qubit and actually transfer them into 2 numbers. So that was the hard part of the lesson. Let's now go back to our presentation. Any questions, by the way, on what we did now? Please, if you have any questions, this is a good time to ask.
I'm sorry, I missed the reduction part from 4 to 2. Could you please show it once again, please?
Yeah, I don't even have to show. I'll just explain. You had 4 different degrees of freedom, right? You had 4 numbers. So the first one to kill is very easy. You know that the squares of the 4 together have to be 1. So you already killed 1, right? You have an equation.
Yeah.
Basically. Okay, so we killed 1. The other one is a little bit more tricky. If we have time, I will show it. I will just mention that it has to do with what we call global phase. Global phase of a quantum number is a number that really doesn't have a meaning. And for that reason, we can get rid of this number as well. Okay, so let's now go back to the presentation. And now it's going to be much, much more easy and more fun. Okay. Okay. So since I told you and you believed me that this alpha and beta, these square numbers here, which each one of them is actually constructed of 2 numbers, right? 2 real numbers, because if this is a complex number and this is a complex number, these are the 4 numbers that we mentioned. But as I said, we reduce them to 2, and go to ChatGPT, it will give it to you in one easy prompt how we get from here to here. But the fact is that you can actually have 2 numbers, we call them theta and phi, which can determine the qubit. So instead of the old A and B that I showed in the last lesson, the real numbers, we can have 2 new real numbers, theta and phi. You can already see immediately that if we take this square and this conjugate square, we get 1. Okay, so it looks kosher already. And if you look at this thing here, you can see that why every qubit is actually a point on the sphere. Since every qubit is only has theta and phi as its parameters, and by the way, theta can be 180 and phi will be 360, then you can see that every qubit, every 2 complex numbers, a vector of 2 complex numbers with a length 1, is actually a point on a very beautiful sphere. Understood? The amazing thing is that the minute we measure the system, the sphere collapses into either being here, a 0 or a 1. We'll show it in a minute. So before we did the measurement, our qubits were floating in a complex world, and each one of them was somewhere on the face of a sphere. The minute we do the measurement, the sphere collapses into a boring 0 and 1. I want to show you a very nice simulations we did for Bloch sphere, and you have the links, so I really recommend, if you have time or if you teach, to play a little bit with it. It's really nice. So what we see here, this is a Bloch sphere, and let's say that we take a qubit 0. Okay? You see that the qubit 0, if it's just 0, it will be something like this. But let's now start to act on it. Now, all these matrices are unitary matrices. So as you will see, they will not change the length of the vector. So now I did a knot, and obviously a knot simply turns it into a 1. Let's do a Hadamard. Okay, this is a Hadamard. And let's just even randomly play with these. And what you can see that each unitary operation simply moves the point on the sphere. And the minute I do a measurement, let's do a measurement, boom, see? It immediately collapsed into a boring blue or a 0, as we said here. Now, if you want to play a little bit with it, it's really, really nice. We can even have a show matrix option here. And let me show you my favorite. Okay, so let's do resetting. Let's reset the simulator. Sorry. And let's take a qubit, which is 0. And now I will act on it with this unitary operation. And the reason I did it is because we're going to use it very soon. What this unitary operation did is it took the 1, 0. Let me just make sure that you see. It took the 1, 0 here, which is our first unit, and multiplied it by this unitary matrix. And as you see, it became a very interesting superposition of 0 and 1, but not an equal one. You can see that the chances to get 0 are actually 75%, 3/4, because if I square this, I get 3/4, and if I square this, I get 1/4, right? So what you see here is a superposition of a vector which has a higher chance to be in the 0 area, and you can also see it here. Sorry, you can also see it here if you play a little bit, okay, with the Bloch sphere. Any questions on the Bloch sphere and why qubits are just points on the Bloch sphere? Great. So I want to show you a nice picture. I don't know if you're familiar with Plato's cave. Plato had a very, very interesting concept, which says the following. Let's say we have a group of captives. You see they're all tied with chains, and all they can do is just look to the front. They cannot rotate their head, just look to the front. And behind them, you have people that are just showing them, just putting above all kinds of shapes. And here we have light. They didn't have projectors in those days, so they just put a fire. And what you see is that these people just see shadows of reality. So reality is really here. Sorry. So reality is here. And what these people are seeing is a very, very flat part of reality. Okay? It's a very deep concept of Plato. And what I would like to claim is that we have a similar situation with the Bloch sphere. Okay? Or in quantum mechanics in general, because we have a whole world which is very full and interesting. And the minute we measure it, the minute we look at it, it becomes a shadow of itself. Okay? So the qubits 0 and 1 are actually a shadow of something which is far richer and more interesting, which is the Bloch sphere. Any questions? Can we continue? Great. So let's do a little bit IBM Composer. And it's not the best simulator out there. The reason I like it is because specifically this composer, we just look for something more interesting. Okay. Specifically, this composer can connect to IBM Cloud. And what it means is that you can actually run things on a real computer. So let's start with some very easy things. Okay. So we have 2 qubits. Both of them, they always start with 0. But what I did to this qubit, I put a knot on it, so I turned it into 1. And what you can see here on the right, what you can see here on the right is that the knot made this into a 1. And if I put another knot, of course, let's put another knot. Of course, it will be 0 again, and they will both have the same color. Now, the reason you see 0 and 0 here is because you have 2 qubits that have the value 0. So the wave function of this whole thing is 0, 0. That's the only state that we have here. What we can also do is use our favorite unitary operation, which is called Hadamard. And Hadamard does something very, very interesting. It takes this qubit and puts it into a superposition of 0 and 1. Can you see here? Okay? Guys, are you with me? Hello?
Yes, yes.
Okay. So what you see here is that I took one of the qubits and Hadamarded it. And Hadamarding a qubit meaning is taking a pure, nice qubit, boring qubit, and forcing it to be a superposition. Now, please understand, when we run this on an IBM computer, on a real computer, we take a qubit and we actually make it a superposition. Now, if I do a measurement now, what do you think I will get if I do a measurement here on the lower one? Of course, I'll get a 0, right? Because it was in 0. But if I do a measurement here, can anybody tell me what I will get if I do a measurement here?
Maybe half 0 and half 1.
Exactly. I have a 50% chance to get a 0 and 50% chance I got a 1 here because the qubit is in a superposition. Now, please understand, what we're saying here is something which is pretty amazing because we have a real random number generator. When I did this measurement, I really have a chance of 50% to get 0 or 1. We never had this in our lives before. I'm reminding you that when we throw a coin, it's not real random. Even when we do a random in our computer, it's not real. We all know that you have to do a seed. But this is the purest random situation in the world, and it comes from the heart of quantum mechanics. It's just pretty amazing. Let me give you one more question. Let's cut this, and let's cut this, and I have a question. What happens if let's do the following. This is very boring. Please tell me what a measurement will give me here.
0.
0, of course, because Hadamard times Hadamard is unit. When we Hadamard twice, Hadamard square is unit. So what we really did here is nothing. But I want to show you something very interesting. What I'm doing now is between these two Hadamards, I'm doing a measurement. What do you think will happen when I release this? Boom. Who wants to explain why? Well, I will.
It's not anymore a unit because when you measure it, you change the value of the first Hadamard, so the total will change.
So I think that you meant right. When we did the first Hadamard here, we have a superposition. But here we did a measurement, so we don't have a superposition anymore. We just have a boring 0 or 1. We don't know what it is. It's either 0 or 1. Now, when we do an Hadamard on a 0 or 1, we get a superposition, of course. So I think it's pretty cool. Think about it. When I put two Hadamards, I get 0. When I put something in between them, just a measurement, I get a superposition. Okay? So now we're going to really cut through the chase and look at the really, really interesting things. And I want to remind you the concept of entanglement. And I think that I told you last time that you really have to destroy after you watch because I'm really doing horrible things. But that's the only way to help you with pedagogics and an intuition of understanding in entanglement. So what I'm going to do now is I have a vessel with red balls and a vessel with blue balls. And what I'm going to do now is I'm going to take a pair, either two red balls or two blue balls. I don't even know what I took. And I'm going to take these three things and these two things and put the balls here. Now, I don't know whether I have two blues here or two reds here, but I know they're the same because I took them from the same cup. Are you with me?
Yes.
Okay. So either I have two blues or two reds. Now, if you remember, according to Einstein, Einstein says, look, it's either they're both red or blue. And the minute you look at one of them, You know that the other one, if this one is red, then the other one is red, of course. But Bohr said something very crazy. Bohr said, no, 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 no. Since we didn't do the measurement, can anybody try to tell me what the wave function of this thing here?
It's half and half, no?
Half and half of what? Let's try to remember what we said in the beginning of the lesson. Remember when I showed you these valleys? We have to start with what will be the final measurements. And we know we can either measure two reds or two blues. After we do the measurement, you agree with me that I either have two reds or two blues, right? So these are the two final steps, the two final possibilities, two reds or two blues. So the wave function, this is crazy, is really once, let's say, half blue blue and half red red. So because I have a half chance, square root of half, yes? Half chance to get two blues and another 50% to get two reds. So the wave function is really a square root of half red red, square root of blue, or square root of blue blue. That's the wave function. Is it understood or not so? Again, remember how we started. I said, when you want to understand what superposition is, look at the system and try to see what the possible classical results of experiment can be. In this experiment, we have two results, red, red, and blue, blue. Do you agree with me?
Yes.
You agree, right? They have a chance of 50%, right? Because I told you that I have, two cups of reds and blues. If I told you that one cup was bigger or one was thinner, maybe it would not be 50%, 50%. But since I didn't say anything, I have 50% of measuring two reds and 50% of measuring two blues. So the wave function of this crazy situation, according to Bohr, is 1 over square root of 2, red, red, 1 over square root of 2, blue, blue. That's the wave function. I know it's crazy, but we'll show it more mathematically in a minute. Now, what I want to show you now is how to do entanglement on a quantum circuit. And please understand the craziness of what I'm telling you now, because everything that we do here, we can actually upload to the cloud and do on a real hardware computer on real qubits. Okay? So what I want to show you now is how I take two qubits, which are not entangled. Obviously, they are not entangled. You agree with me? But let me prove very easily. Let's do the following. Let's do here Hadamard and here Hadamard. Okay? Okay. Now see, we have, so both of them can be, have a 50% chance of being 0 or 1. You agree with me? Now let's measure this one. I'm measuring it. I'm measuring the first one. It came blue, but nothing happened to the lower one because they are not entangled. They don't care about each other. Entanglement is when you look at when you measure one of the particles and the other ones automatically collapses. Just going back to this example, if I now look here and I see that I have red here, this one automatically becomes red. It's not a superposition anymore. So the minute I looked here, the wave function collapsed here. That's the idea of entanglement. So what I would like to do now is to show you how I can create very easily entanglement with this. Okay, so the way I do entanglement is the following. Before we go deep into it, I want to introduce a very interesting operator, which is called control not. Control not. What is control not? Control not means, please look at this qubit here. Let me show you. Let me just grab. This is the control not. Okay? What this means is the following. Please look at Q0, at the first one. If it's 0, don't do anything. If it's 1, change me. In other words, Q1, what this means is the following. please look at this one, Q0. If you get a 0, don't do anything, which is, by the way, exactly what happened here. This one was a 0 and it's still a 0. But if this one is 1, if the control bit is 1, please do a flip on my state. Let's test it. Let's put a knot here. And before I release, what will happen when I do a knot here? The upper one will become a 1, right? But now the control sees a 1 and will make the other one a 0. Okay? Sorry, we'll make the other one a 1. So let's see what happened now. Now, when I did this part, this guy became a 1. But what is a controlled? Controlled knot says if you see a 1 here, change me. If you see a 0 here, don't do anything. It's critical that you understand this. Okay, it's very simple. First of all, it's an interesting way to connect two qubits. It's the first time that we see an operator that connects two qubits. And by the way, this is already a 4x4 matrix, but we will not get into it. So what I did now is I introduced an operator which looks at one qubit, sees if it's a 1 or a 0, and accordingly decides on what to do to the main qubit, which is Q1 here. Please let me know if you need some more explanation on Q0, because otherwise you will miss the whole point of the lesson today. So I'm assuming you understand. Now I'm going to do something really, really crazy. I'm going to put a Hadamard here. And if you remember, putting a Hadamard here turned this Q0 into a superposition. So now it's half-half. It's half 0, half 1, right? But what will happen if I do a controlled knot on this one? You know, maybe before that, I want you to look at this thing here at the bottom. This one is a combination of 0 and 1, and the one on the bottom is only 0. So the two options that we have is 0 and 0 and 0 and 1, because this 0 can be before the 0 here and can be before the 1 here. So actually, we have the state or the wave function of the system is very simple. It can be either 0, 0 or 0, 1. This is always 0, right? This is a 50% of being a 0 and 50% of being a 1. So basically, we have 50% of having 0, 0 and 50% of being 0, 1. So that's really the wave function, a combination of the two. Now I'm going to do something which is really, really crazy, and I'm going to do a control knot here. Wow. So let's first of all try to understand what I did here. I'm going to qubit
Why
0.
the Q0 changed?
Oh, beautiful question. Very good question. First of all, how do you know that the Q0 changed? It was a superposition before. We had the Hadamard.
I saw the diagram has changed on the screen.
Okay. So this is really a miraculous thing that you're looking at now. Remember, what is the idea of control knot? As Liron said very smartly, when you look at the idea of control, especially in classical system, is you look at Q0 and ask Q0, what are you? Are you a 0 or a 1? And then act accordingly. If you're a 0, do nothing. If you're a 1, change. But what we have here is a crazy situation where Q0 is two things at the same time. It's a 0 and a 1. So how can you ask it, are you a 0 or a 1? Right? And the answer is, it's a linear combination, okay? So the 0 part does nothing, and the 1 part makes the change. And what it means, if you look here now, And this is a very dramatic thing. We now don't have a wave function. We don't really have a qubit for each qubit here. They're entangled. They became one animal, one monster. And the wave function now is 0, 0, 1, 1. Okay, and let me explain why again. Remember, this started as a 0, the one at the bottom, right? Now, we looked at the one on the top and asked it, are you a 0 or a 1? So he said, look, I'm both. Okay, no problem. So we start with a 0. Are you a 0? Yes. So I'm not changing. So I'm staying a 0. So this is the 0, 0. But now we look at the one part of the first qubit, and now we have to change. Okay? And we have to change to a 1 because we were a 0 before. So now we have what we call an entangled situation. So first of all, if you remember that I told you that the wave function of these two was 1 over square root of 2 blue, blue, plus 1 over square root of 2 red, red, this is exactly what you see here. It's the 0, 0, and 1, 1. And to finally prove you that we are entangled, maybe one of you would like to offer an idea how we can prove by one little control here that these particles are entangled. What do you think we should do?
Maybe if you put Hadamard on the Q1, the first the Q0 will change also.
I can put an Hadamard, but how will I know that whether we entangled or not? You remember that I told you there's a very simple way to tell whether two particles are entangled.
That if you change the value of one of them,
If you measure, let me correct you.
if you measure one of
one
them,
of
the
them,
other one also.
the
I
one of
mean,
them
if
will
you
collapse.
measure Q0, you will
Beautiful.
see that Q1 also got measured.
Very good. So let's try it. Okay. Are you ready? Let's measure the upper one. 1, 2, 3, go. Beautiful. Do you see what happened? The minute I discovered that this one is blue, the other one automatically became blue. It is no choice. It's like the two reds that I have here. If I found here a red, this one must be red also. I know it's not easy, but please understand the greatness of what we are seeing here. We're seeing a very simple circuit which we were able to prove that it created entangled qubits. And the amazing thing is that we can do it with real hardware qubits. I can upload what you see here to the cloud, wait a few minutes, and somewhere in North Carolina, two qubits will be entangled. Okay? Okay, let's move forward. So we played a little bit with the IBM Composer, and now we're really getting to the crust of the lesson. And that is, don't be afraid, we don't have to do this part, and that is teleportation. So first of all, I want to tell you what is teleportation, okay? Teleportation is a situation where you have two people that can be light years away, and you have a particle that you can transfer from one person to another. In this case, this one is called Sally, this one is Bob. And what we will show is that Sally and Bob will actually go to Mars, okay, which is 12 minutes. It takes a photon 12 minutes to reach Mars. And what I will show is that Sally has a way to take a qubit and move it to Bob almost immediately. Now, when I say a qubit, please remember the Bloch sphere. It could be any point on the Bloch sphere. Of course, there's infinite number of qubits in the world. So imagine there's a certain qubit on the Bloch sphere, And what we will show you now is that Sally can transfer this same qubit to Bloch. Okay, so first of all, how do we do it? The first thing we do is before Bob goes to Mars, each one of them takes a particle and they entangle the particles. So, sorry. What you see now, I just imagined, a device which does the entangling, and the minute they activated this device, boom, their particles are entangled. And by the way, you can see it's exactly what, if you look at the bottom, you can see that's exactly the circuit that we have, which created the entanglement. H, okay. Now, let's see what happens. They're entangled, everybody is happy. Now Bob is going away on a spaceship. You see that they're still somehow connected. They have this beautiful quantum telepathy, the entanglement. Now he's in Mars, and they're still somehow magically connected. But what Sally wants to do is use this connection to transfer a qubit to Bob. And let's see how she does it. Now we have this guy from Federal Express or Interstellar Deliveries. He has the particle that we want to transfer to Bob. So this green particle, it has nothing to do with the first two particles, right? This green particle now is about to be transferred to Bob. Now, the way I did this green particle is I took Q0 that you see here is really the green particle. And what I did is I took an operation which makes it a little bit more interesting, not half-half. It's the 3/4 quarter one that I like, the 0.3/2 and 1/2. So what I did here is I took the original 0 qubit, put an operator on it, which we'll see together, and made it this particle. So let's look at the circuit that we have here. These are the two original entangled particles, only they're 12 minutes of light years away. This one is in Mars, and this one is on Earth. Okay, do you understand? Yeah. So the bottom two qubits are the two qubits, the original two qubits of Bob and Sally. The one on the top is the green one that we want to transfer to Bob. Great. So let's see how we do it. So what Sally does now, she takes that particle, the green particle, and she doesn't measure it. It's very, very important to understand. No measurement. But what she does, she entangles. She put the entangler on it, and now something really interesting happens. Sally is entangled both with Bob, the original entanglement, but she's also entangled with the new particle. Okay, what you see here in the red square here, these are the circuit elements that created this entanglement. So the entangler that she has here is actually these two very boring unitary operations that you see here. And now all three particles are entangled. It's amazing. So this telepathy that we talked about is now happening between the two particles that are, right close to each other, the green one and the original Sally one. But as you can see here, it's still going all the way to Mars. Okay, are we okay? So what Sally did, let's do a quick repetition. We started with entangling Bob and Sally and then sending Bob away. So, and both of them, like Eshet Lot, did not do a measurement. They were very strong because the minute they would measure, the whole thing would collapse. So they still have these two particles entangled unmeasured. Now a third particle is coming, the green one, and Sally entangles it with her particle. So Sally's particle is really entangled with two particles, with the green one and the original Bob. Believe it or not, we're practically done. Now, Sally is going to do something really crazy. She's going to open both boxes. She's going to measure the two particles that she has. Okay? She opened it. Okay. The first thing we know, these are the two measurements, of course. Now everything is boring here, right? She measured. It's either 1 or 0. What can, we know that measurement brings us to the shadow of the beauty of quantumness. So she did two measurements here. We always get a 0 or 1 when we measure. But please look at this crazy thing. Remember this original green? The minute she did the measurement, it somehow went all the way to Bob. This is Bob, remember? This is Bob in Mars. But to those of you that have very good eyesight, you can see that they're not really the same. If you look at this picture here and this picture here, you see that there's a black line here and a black line there. So for physicists, it's a phase issue, but basically something amazing happened. The minute she measured, some kind of a signature of the green particle immediately, instantly appeared at Bob's box. So the particle in Bob's box is not what it used to be, okay? It used to be just boring superposition, as you can see here. And all Sally did was just measure, just open two boxes on Earth, on the table in her garden. And the minute she opened them, something dramatically happened to Bob, but not what we expected. We would expect it to be either 0 or 1, red or blue. But for some reason, something about the nature of the green qubit went all the way to Bob. So you could say that, wait. Einstein, remember the argument between Einstein and Bohr, and Einstein said you cannot move something faster than the speed of light, and Bohr said, true, but if I'm not moving information, I can do things instantly. This seems to be information. I mean, if you think about it, everything here happened instantly. The minute she measured, boom, Bob's particle became very similar, and that's the trick you'll see in a minute, very similar to the original particle. I can tell you that if they would be exactly the same, we would be in great source. I mean, physics would collapse. But they are not exactly the same, and now something very interesting happens. And what I'm showing you now is the protocol of teleportation. How we do teleportation, and just to be sure, let's start from the beginning to make sure we understand, okay? So we started with two friends. They entangled their particles. One of them went to Mars. They never opened the boxes. They have this beautiful quantum telepathy entanglement connection between them. Now comes the delivery guy with the particle that he would like to teleport to Bob, the green particle. What Sally does is simply entangle her original particle with the green particle, measure, and now comes something very interesting. After she measures, she sends a WhatsApp to Bob. Hi, Bob, I measured 0 and 1. Remember, she had two particles, right? So in this case, she measured 0 and 1. And Bob say, thanks, on it. Do you see anything strange about this WhatsApp? Look at the timestamps. One would say that, okay, he's a man who meyabesh. I mean, why would it take him 12 minutes to answer?
It's the length on a light year.
Because it takes 12 minutes for a photon to reach from Earth to Mars. Okay, that's the fastest way to connect between two people that are 12 minutes photon time away.
So she should see it after 24 minutes.
You're right. Good point. Very good point. It should be a 24 minutes because it's 12 both ways. But what you see here is that she sent a WhatsApp and it reached Bob after 12 minutes, right? And then something magical happens. She told him, remember, she told him that she measured 0 or 1. She could measure 1, 1. She had 4 options, right? Now, Bob has a table on Mars which says the following. If Sally would have told him that she measured 0 and 0, do nothing. You see, you have a unit matrix. Do nothing to this particle. If she measured 0 or 1, do a not to the particle, sorry. Operate with a not on your qubit. Remember, we don't know what the qubit is. We never measured it. If she measured 1 or 0, if she would tell you by WhatsApp it's 1, 0, then just do a Z, and otherwise do an X and a Z. So just understand the protocol, okay? Let's see it from the beginning. Not from the beginning, but from this part, okay? The minute she opened the boxes, obviously 1 is 0 or 1. They could be 1, 1, 0, 0. We have 4 options, right? All she does is send Bob the information of the results of her measurements. Which one of the 4 she measured? When Bob gets the information after 12 minutes, all he does is say, okay, she said 0, 1. He takes an X operator, see, just takes the X, boom, operates on his qubit, and look at that. He gets the original qubit. So if the original qubit, the green one, was alpha 0 plus beta 1, what happened is he recovered the alpha and the beta. Now, please see that before that, he really had something wrong. He had alpha times 1 plus beta times 0, which is similar, but remember the original one was 0 here and 1 here. But the minute he did the X operation, it really became the right one. You understand? Because if you operate with a not, on this qubit, what happens? The 1 becomes a 0, and the 0 becomes a 1, right? So the alpha now is in front of a 0, and the beta is in front of a 1, which is exactly what we have here. So basically, this is the protocol. And what I would like to do with you very quickly is show you the real circuit that does it. I just want you to see how simple it is. Okay, just want to show you. This is really the circuit. Okay, this is the circuit. Now, these lines that you see here and these pictures that you see here are not a part of the circuit. They're just helping me to see things. The real circuit, if we remove them, is that simple. That's the whole thing you need to do teleportation. Okay? The first part, this part, is doing the initial entanglement. The second part is doing the second entanglement. Measurement 1, measurement 2, phone call or WhatsApp, and then Bob does the 2 operations, and that's it. So let's just look at it in real life. Okay, this is now the real circuit, and I want to show you a very nice trick in the IBM tool, which is called inspect. So what I'm going to do here is go through the circuit step by step. Okay, so so what I did now is I did this part. Let's look at what we have here. So look, it's a little bit confusing, but don't worry, okay? Here we have Q2. Q2 is still 0 here, right? Because I didn't do anything to it. So Q2 is 0. Q1 is half 0 and half 1. And here, what I did is I took a qubit and made it 3/4 and a quarter, okay? This is the operation which I can show in a minute. So what you see here until now, everything is very boring. We have a 0 here. We have a 0 and 1 here. And here we also have a 0 and 1. And for that reason, we have 4 options. And the reason they are not equal is because we have a square root of 3 and a quarter. So this is what I get on this stage. Let's take another step. Ooh, now I did the knot. So now we already have entanglement. Okay? So this is the result of the entanglement. And if we want to see, we can see here the result. This one I didn't entangle yet, so it's still in the 3/4 and quarter state. But these two are entangled. Now, I'm going to do the second entanglement. So I'm going to entangle this guy with Sally. So let's see what it looks like. I have to do a controlled knot, a Hadamard. And what I get here is 3 entangled particles. Okay, let's do the measurements. Measurement number 1. Now, I did both of them. And what you see, again, amazingly, is that I didn't do the call yet. Everything I did here is local, okay? Sally didn't call Bob yet, okay? But what you see is that immediately after I did the measurements, the original green particle here almost came here. I'm saying almost because it has a different phase. Okay, if this would be exactly like this, physics would break forever because it means that I can move information faster than the speed of light. I'm reminding you, at this stage, I still didn't do any WhatsApp or any call. So this was instantaneous. But fortunately, it's almost the same. And in order to really make this guy be like the original one, we have to have the WhatsApp call and the 2 operations. And please look at this now. It will soon become like the original one. So, beautiful. You see now, Bob's particle is exactly similar to the original green particle. Okay, I know it's not easy, but I do insist in spending 5 minutes to show you the mathematics. If you don't get it, it's not a big problem. Just go over it, go over the lecture, because it has some really, really deep stuff in it. So now we're going into the mathematics of the whole thing. And trust me, if you go through it and you understand the deck and everything we talked about, you really understand teleportation. And it's not an easy thing to understand. Okay, so let's try to look at the mathematics of what we did. And as you can see, I just went to ChatGPT and told ChatGPT, give me the protocol of teleportation. And he said, okay, qubit 1, which is the green one to be delivered, is alpha 0 plus beta. So that's the general particle, the green particle that we talked about, that has to be transferred. Qubit 2 and 3 are the Bob and Sally particles. And as you can see, they're already entangled. So ChatGPT says, look, I don't care about, let's start with them entangled already. So he's already in Mars. In other words, ChatGPT starts from this part here. Okay? He doesn't care about how exactly Sally did the entanglement. Okay? So ChatGPT says, look, we have 2 entangled particles. Remember the red, red, and blue, blue that I showed you with the boxes? We have 2 entangled particles. By the way, you can see immediately that if you measure the first particle here, let's say the particle on the right, then if it's a 1, the other one immediately has to be a 1, and vice versa. So this is a real example of entangled particles. Now, since you have this wave function and this wave function, the true wave function is a combination, The true wave function is what you see here, is alpha 0 plus beta 1, which is the green particle, times the entangled wave function. It's just, simple Amora Ruti mathematics. You just פתיחת סוגריים, and you get this thing here. So really the wave function before we did the second entanglement is what you see here. Okay, we have 3 particles. Okay, so now let's try to do the second entanglement. And I want to remind you the second entanglement had 2 steps. The first step was a C naught. And what's a C naught? C naught means that you look at the digit on the left. Do you see my cursor? Do you see my mouse cursor?
Yes.
Okay. If it's a 0, do nothing. You see, I have a 0 here, and I'm doing nothing here. So these 2 are do nothings. But if it's a 1, change the other one. So this 1, 0 becomes 1, 1, and this 1, 1 becomes 1, 0. So all we did now is change this wave function to this one. And the reason we changed is because we see that everything that starts with a 1, 0 becomes a 1, 1. See, this one is a 1, 0, and it becomes now a 1, 1 here. Okay? Are you with me? Okay. The next, maybe just to make sure you understand, the C naught that you just show is really this one. Okay, it's the second one because the first one ChatGPT doesn't care about. It says, I don't care about this initial entanglement. Let's start with them entangled. So what we saw actually is just this C naught. And now all we have to do is this Hadamard. And we finished. Okay, so we did the C naught and now we do the Hadamard. Okay, the Hadamard is a little bit more complicated. To remind you, Hadamard on a 0 does this, and Hadamard on a 1 does this. So what we're doing is we're just doing a Hadamard on the green particle. And here really comes the magic. I really want you to look at this page because this is really the true magic of quantum computing. So all I did was something very simple. This is h. I'm multiplying each one of these by h. You agree, right? I did a C naught. That's the result of a C naught. Now I am Hadamarding. So I have a Hadamard here, a Hadamard here. I have 4 Hadamards. Okay? Let's see now what happens with these Hadamards. Okay, so the first Hadamard, you see, I can put the alpha on the left because the alpha is just a number, right? I can put it on the left. It's not, we're talking about linear stuff. So I'm doing the Hadamard on the 0, and Hadamard on the 0 is simply 0 and 1. I open the parentheses, and this is the result. So the first element, when I put the Hadamard on the 3 zeros on this one, okay, this is what I get. It makes sense that I get 2 parts because Hadamard is divided into 2. And this is the second. Let's do the second. Let's do the third. Okay? So the third is 1, 1, 0. Let's look at it. Okay, sorry. Okay. I have a beta 1, 1, 0, and I want to Hadamard it. Okay? So let's see what happens. Okay? I had the 1, 1, 0. I'm Hadamarding the 1. Hadamarding 1 simply gives me this. And this is why we get the minus here. But everything we see here makes sense. You agree with me, right? But what I'm doing now looks like a very, very innocent trick. Okay? What you see here is really the combination of the 4. I have 1, 2, 3, 4. I'm just combining them. But I'm doing a very weird trick. I'm taking the alphas and betas and pushing them to the right. I can do that. It's a number. And when I do it, I can do another trick. Let's look at, you see that I have 2 zeros here? I also have 2 zeros here. So I'm taking them out. I'm taking the 2 zeros out, and this is what I get. Let's understand why. I have 2 zeros here, and I have 2 zeros here. I'm taking them out, so I have here alpha over 2 and beta over 2. Let's see what starts with a 0, 1. I have a 0, 1 here. Let's look for, and I have another one here. So I'm taking it out of the parentheses, and I get, of course, again, alpha 1 plus beta 1. That's all I'm doing. Simple Amora Ruti arithmetic. But the result is really astounding, because these are the two particles that Sally has. And what you really see here is really the miracle of teleportation. Because if Sally measured 0 and 1, everything becomes 0 because we collapsed. So everything is, all these other three collapse, and we are left with alpha 1 plus b 0. If she measured 1, 1, then all we have is, that's the only thing that's left. So this is Bob's particle. I know it's difficult. I know it's difficult. Let me repeat this in 1 minute because it's worth it. Okay. What we did, we arriving here is just simple mathematics of doing a C naught and a Hadamard on a wave function. And by very simple arithmetics, taking things out of the parentheses, we found out that we can write the wave function as this is some kind of a complex number times this wave function, and this. Now, these are the particles that Sally has, these two. The minute she measures them, that's it. We don't have four options. We don't have 1, 1, 1, 0. We either have 1, 1, 1, 0, 0, 1, or 0, 0. That's it. So let's say she measured 0, 0. If she measured 0, 0, it means that Bob particle is the original particle. Remember, alpha 0 plus beta 1, that's the green. So if Sally measured 0, 0, all she has to tell Bob, do nothing. You have the final particle. But if she measured 0, 1, please see what happened here. Alpha now, instead of being before the 0, it's multiplying the 1. So she tells Bob, wait, to get the real green particle, you have to do a naught here. Because what does a naught do? It takes this 1 and turns it to a 0, like we have here, and this 0, it turns it into a 1. So what Sally now is doing by making the call, once she did the measurement, everything here collapsed to one piece, and now she's doing the call, and once she does the call, she knows how to fix things, because if she measured 1, 1, she knows that what Bob has to do is first of all to make a plus here, and then do a naught on the 0 on the 1. So now that you understand it, let's quickly look again at the whole thing. Now you will even better understand it. So we started with entanglement. He went to Mars. They're still connected. Now somebody wants to transfer the green particle. We're all very happy. She's entangling the green particle also. All three are entangled. Now she does the Eshet Lot thing. She measures them. Boom. The minute she measures, now Bob's particle is one of four, depending on the results of her measurement. Okay? If she says, I measured 0, 1, he looks at the tablet, and that's what he has to do, and not. Remember, if she measured 0, 0, we said that he has the original one. Do you understand? I know it's difficult, but do you need more repetition, or are we more or less there? Okay, so I'm assuming that you are more or less there, and I would like to end this lesson. And by the way, we're ending this course because this was the last lecture. I would like to end with a question, a deep question. We all agreed that after we did the two measurements, Bob's particle became pretty much similar to the green particle, right? It had, by the way, a 25% chance to be exactly this particle. But specifically in this example of 0, 1, it became like. But do we really need the call? Do we really need the phone call? Because I could say the following. Let's say that before Bob left to Mars, I told him, look, I may send you a particle which has a 75% to be 0 and 25% to be 1, an uneven particle. What I'm going to do is tell you to measure But I'm going to send you not one particle. I'm going to send you 1,000 particles that are exactly the same, 1,000 green particles. And all you have to do on your side is measure. Don't wait for a phone call. And what I would almost say is that if he measures, if he does thousands of measures, let's say I sent him 1,000 green particles, and he does these measurements, he may be something uneven. And if it's uneven, then I sent him information faster than the speed of light. So please see, this is deep stuff. Now assume that he's 20 light years away. He's on another star, okay? And I'm telling you, listen, Bob, before you go, I may at a certain time send you 1,000 particles. Measure all of them. If you see that they're uneven, it means that I like you. So I found a way to send a message to Bob instantly. Instead of waiting for 20 years, you will get it instantly. All he has to do is just very quickly measure. So where do you think is the problem in my idea or trick here? Okay, you can see this maybe. Okay. These are the 4 options. Remember? What will happen if he does 1,000 tests? He will get half again. He will not get the 3/4 and 1/4. Because it all averages out. So he will do 1,000 tests. And in 50% he will get 0 and 50% will get 1, meaning that we were not able to send him a message. Isn't it beautiful?